we're gonna start now a new chapter. So here we're gonna the main idea is that we're gonna talk about infinite series. But before we understand series, we need to have a small discussion about sequences. Okay, so sequences. This is basically very similar to what you saw in part one about limits. So it should not be too bad. Okay, so let's discuss sequences first, and then we'll worry about series. The point is that we need sequences to make up series. Okay, so that's the point. All right, so let me start with a definition. So what's a sequence? You know, the informal definition is a sequence is just a list of elements. Okay, in our case, we're going to be working with numbers, so we'll just be a list of numbers. But I'm going to give you a formal definition. Okay, so basically, a sequence is a function. So a sequence is a function with domain the natural numbers. It's a function whose domain is the set of natural numbers. Or a subset of it, okay? But let's just say natural numbers, or you could say the positive integers, etc. It's a set of natural numbers. In other words, you can think of a sequence as a function that goes from the positive integers, or you could write here the natural numbers n, however you want, to some set A, okay? This is a set. And basically, this is a formal way of saying that you're going to have a list of elements from this set, and then the first element is the output of 1, the second element is the output of 2, and so on. Okay? So basically, 1 is going to be mapped to f of 1, which we typically call it A1. 2 is going to be mapped to f of 2, which we typically call it A2, and so on. In general, n is mapped to f of n, which we typically call it an. And this is an infinite sequence because, as you know, the positive integers or natural numbers, they are infinite. Here I started with 1, but in many cases you're going to see that sometimes sequences they begin with 0. Okay, so but it doesn't really matter whether you begin with 1 or 0. You can always adjust your problem to match the given situation. So we typically write a sequence as follows. Instead of writing the function on f of 1, f of 2, etc., we like to use this a1, a2, etc. notation. And you should understand that what this means is this is the output of 1. So this is the first element in the sequence, this is the second element in the sequence, and so on. So we use the subscript to talk about them. So we normally write it like this. Okay, so we write an in between curly braces. Sometimes, if we want to be specific, we will say this by saying that n starts at 1 and goes all the way to infinity. And this stands for, you know, the list A1, A2, A3, etc. Okay, an, and so on. Just a list of elements. And here this could be numbers, functions, whatever you want. In our case, we're going to be working with numbers. Okay, so set A will really just be real numbers. But it doesn't have to be, it could be functions or something else. Okay, so these are the objects that we want to study, just sequence of elements, okay? And in this case, a list of elements, in this case would be a list of numbers. Let me give you some examples. So you have something, you know, to refer to. So I'm going to give you some sequences. I want you to tell me the first 5 terms, okay? So determine the first 5 terms. And then, let's see, let's put the sequence an. This is given by 2 plus -1 to the n. And I'm going to put here the sequence bn is given by n, or 1 minus 2n. Let's say here n begins at 0, so from 0 to infinity. And this one, I'm gonna start at 0 as well. And then let's say 3 cn would be n squared over 2 to the n minus 1. And this time, let's start this one at 1. Because if I start at 0, that's a problem, because 2 to the 0 is 1, 1 minus 1 is 0, so it's not defined, right? So basically all I'm doing here is I'm giving you the formula that we're gonna use to get the terms of the sequence, but you need to understand that the inputs are natural numbers, okay? Because really what we're defining here is a list of elements. So let's see, let's write down the first 5 elements. So that means n is like a counter. So when n is 0, that's your first element. When n is 1, that's your second element, and so on, okay? So what are the elements in this sequence? What's the first element? You get 2 plus 1, right? Because negative 1 to the 0 is 1. Yes? So you're going to get 2 plus 1, which is a 3. What's the next element? 1. So the next element is going to be 1. Very good. Because when n is 1, you get 2 minus 1. What's the next element? 3. 3 again. So basically, when n is even, what's going to happen? You get 2 plus 3, right? Because you're going to get negative 1 to an even power that's positive 1. When n is odd, you're going to get 2 minus 1, which is 1. So this is just a sequence of 3s and 1, 3s and 1, 3s and 1. This is just a fancy way of saying 3, 1, 3, 1, 3, 1, and so on. Do you understand this? So when n is even, and remember this is for n equals 0. This begins at 0. Okay? The point is that when n is even, we're going to get 3. When n is odd, we're going to get 1. So the first 5 elements are 3, 1, 3, 1, 3. Questions? Okay, the next one. What are the first 5 elements?
Is that 2n at the bottom?
2n.
Oh. 0, 0 at the end.
So begin with 0, then
1 over negative 1, so negative 1.
So negative 1, then
2 over negative 3. So negative 2 over 3.
Then when this is 0, 1, when this is 2, what do we get? We get 2 over negative 3, yes? Then?
Negative 3 over, negative 3 over 5, negative 3 over 5.
So that's 0, 1, 2, when it's 3, that's going to be 3 on top, and then negative 5 in the bottom, right? Let me put it negative 2 over 3, negative 3 over 5, and then the last one will be a 4 on top, and then in the bottom we're going to have 7, so negative 4 over 7, and so on, right? Again, this is just to understand that the sequence is, it typically is given to you as a formula, but you need to understand that this formula just represents a list of numbers. That's all it is, okay? That's all it is, a list of numbers.
Sort of like an array.
Yes, but it's an infinite array. Okay, questions? Do you understand this? Okay, the next one. What are the elements? Let's just finish this. So when n is equal to 1, we're going to get 1, right? Then when n is equal to 2, what do we get? We get 4 over 3. Then when n is equal to 3, what do we get? We get 9 over 7. And then when n is equal to 4, that's a 16 over 15. And finally, when n is equal to 5, that's a 25 over 32 minus 1. It's a 31, right? 31?
Yeah.
And so on. Okay, so sequence is just a list of elements. So it may be given to you like this. When it's given to you as a formula, it's very nice. You know everything about the sequence. But many times, they don't show up like that. For example, you may be given a sequence in this form. Let's say d1 is equal to 0, d2 is equal to 1, and then I define dn to be dn minus 1 plus dn minus 2, as long as n is 3 or bigger. Here's an example of what we call a recursive sequence, okay? It's recursive because we're using its own terms to define new terms, okay? So notice that here, basically I'm saying if you want to know the next term is the sum of the previous two. That's what this means. If you want to get the nth term, you need to add the n minus first term and the n minus second term, so the previous two. That's why I have to tell you how to begin the sequence, because if I only give you the formula, how do you begin? You need to know two terms. So I give you the first two guys, and then you can build this up. This sequence has a name. Anybody recognize it? Yeah, this is the Fibonacci sequence. It's called the Fibonacci sequence. Okay, so what are the terms here? So we have 0, we have 1. What's the next term? 1. Then
0, 2.
No, 2. To get the next term, you add the previous 2.
Oh, I was subtracting.
Right? You add the previous 2. So you get 2, then 3, then 5, 8, 13, and so on. So, for example, a typical question is, can you find a formula for the Fibonacci sequence, a closed formula? Because you see, if I want to figure out what's the 100th term in the Fibonacci sequence, by using this definition, you first need to know what's the 99 and the 98th term to be able to get to the 100th term. So you have to compute all terms up to that so that you can figure out the 100. It's not like this one, like number 3, for example. If I want to know what's the 100th term, you go plug in n equals 100 and then you're good, right? So it's nice to have a closed form like this. So sometimes this one, it requires some knowledge to be able to figure it out. It's possible to do it. It's possible to find closed form, but you need to know infinite series. So we may be able to do this towards the end, once we finish up this question of series. Okay? Then we may come back to this and find closed form for this. Anyways, but just keep in mind the sequences, they may come in different forms and shapes. Okay? This is an example of a recursive sequence. Okay? Okay, questions on what a sequence is? Are you okay with this? All right, so now one typical question, this is calculus, right? Given a sequence, we would like to ask for its limit, okay? In other words, how big do the terms of the sequence get? Or as n, when you go, so here the way to think about it is when you go deep into the sequence, are the values of the sequence getting closer and closer to some particular number, okay? So when n is very big, remember that n here stands for the index, the subscript that we're using. Okay, the bigger n is, that means the deeper you are into the list, into a sequence. You understand this? When n is 1,000,000, you're looking at the millionth term in that list. So when n gets very big, what can we say about these terms? Are they getting closer and closer to some value? If this happens, then we call this the limit of the sequence as n approaches infinity. The limit equals that number. Just like what we do with functions, right? Functions, you look at x. Here we look at n. Do you understand this? The sequence is a function anyways. Okay? Because we typically don't talk about it like that, but it is a function where the input are natural numbers. So let's talk about limits. And so limit of a sequence. Limit of a sequence. And you know, since you already have the intuition of limit from Cal 1 when working with functions, then this extends very nicely to sequence. So for example, let's look at the sequence. You know, most of the time we just write this down and it's understood that we're talking about a sequence. Basically, an is called the general term. So an, we typically call it the general term of the sequence because it's the one that tells you how to get, you know, given n, how to get the other terms. So let me say this an, we call it the general term of the sequence. If we have a formula for it. Like in the first 3 examples that I gave you, we had what I was giving you was an. I was telling you what this guy is. Okay? That's called the general term. It's the same type. Why do I keep changing this? Okay, so in this case, if I say an equals 1 over n, that means I'm talking about the sequence 1 over n, where the terms have the form 1 over n. Okay? So in other words, here I'm talking about the sequence 1 over n. When it's understood, we don't write the 1 and infinity and so on, but you know, or if you want to be clear, then just write it down. Basically, here we're talking about the sequence 1, 1/2, 1/3, 1/4, and so on, right? And so, you know, the question is, what can we say about the values of this, right? Are the values of this sequence getting closer and closer to something when n gets larger and larger? So it gets closer and closer to 0. So we say the limit of this is 0. You understand this? So it's very similar to what you're used to with functions. So the question is, now you need to understand that for functions, we had the notion of limit as x approaches a number, right? This doesn't apply here because here your input, all it does is it goes towards infinity, okay? So here we're just talking about infinite limits as n approaches infinity, okay? Okay, so are the values of the sequence getting closer and closer to some value, to some number, getting closer to a fixed number as n gets bigger, okay? As n gets bigger. And then, as you all know, the answer is yes, and then it gets closer to 0, okay? So we write this in different ways. So we write, so many times we just write the sequence 1 over n approaches 0 as n approaches infinity, and this is sometimes it's even optional because it's understood that the only thing that we're doing is n approaching infinity anyways. So you just write the arrow and that's it. You could also write an approaches 0, you can write that as well, or more formally, limit as n approaches infinity of an equals 0. Then of course, in this case, an stands for 1 over n. Right? All of these are different ways that we write, but you know, it's a lot of letters to write limit and so on. So we typically just use the arrow notation. So you're gonna see me using the arrow notation in many instances. Okay, not always, but in many instances, I'm gonna use the arrow notation because it's fast. Okay, so let me go ahead and then define this formally, because remember, you have a definition for limits of functions, right? Using epsilons and deltas and so on. That's what I'm gonna do now for sequences. Okay, I'm gonna give you the formal definition. But keep in mind, all I'm gonna do is mathematically, I want to express the idea that we're getting closer and closer to something when n is very big. That's all I want to say. Okay? And if the limit exists, we say the language that we use is the sequence converges and converges to that number. If the limit does not exist, we say the sequence diverges. Okay? Just like what you saw for intervals. Okay, so definition. This is the definition of limit. So let an be a sequence and L be a fixed value or real number in this case. Let me say value. Fixed value. Okay. Then if whenever we write limit as n approaches infinity of an equals L, whenever we write this means the following. So it means the following. For every epsilon, I'm going to explain what this is. Let me just write it down. So for every positive epsilon, there is an n, capital N, which is positive, such that for all little n greater than or equal than this big N, the absolute value of an minus L is less than epsilon. So let me explain to you basically what I'm saying here. So remember, we want to express mathematically the fact that the terms of this sequence are getting closer and closer to this number when n is very big. So what does that mean? That no matter how far you're going, no matter what number you give me, okay, we're going to play the following game. If you're telling me that this sequence is getting closer and closer indefinitely to this number L, it means that I should be able to pick a very small number, and then you should be able to find elements in your sequence so that the difference between those elements and this L is less than the small number that I picked. Because after all, they're getting closer and closer to this L, right? So if I pick 0.000000001, you should be able to find terms in your sequence so that the difference between those terms and L is less than that small number. That's what it means to get closer to something, right? Otherwise, you're not close to L. You're close to L minus 0.0000001. Okay? So that's basically what I'm saying here. In other words, for every positive number, the understanding is that this epsilon should be something very, very, very small. So no matter what number you give me, I should be able to find another number, let's call it n. Now, this stands for how far into the sequence I need to go, such that from that point on in the sequence, so for all little n bigger than this n, I'm talking here about the index of the sequence, starting at this point in the sequence, every term, the difference between that term and L, so the distance, remember that survival is distance, the distance between the terms of the sequence and this number L is less than this number. And you can play this game for every single number. Of course, if you change epsilon, this n is gonna change, okay? And you may have to go farther into a sequence to now get closer. Sometimes it would be enough to go 3 terms into a sequence and then you already have the distance that you want. Sometimes you need to go 1,000 terms into a sequence and you have the distance that you want. But it doesn't matter, n goes to infinity anyways. So that's all I'm saying here. But this is, and this, you have a similar definition for functions when you discuss limits, okay? It's just that it's more complicated because this is the limit at infinity, but when you approach a number, then what you want to say is when you're very close to this number on the x, then on the y, you have an inequality like this one. So there's an epsilon, there's a delta, and all stuff going on. Anyways, all I'm saying here is that we have a notion of limit, and this notion of limit agrees with the notion of limit that you have for functions at infinity. Okay? The same way that you calculate limits at infinity with functions, you can use that technique for sequences. And the good news is that we have a theorem that says precisely that. So theorem. So let L be a real number. So let L be a real number and f a real value function with the condition that the limit of the function is L, with limit as x approaches infinity of f of x is equal to L. Then if we have a sequence, so if an is a sequence with f of n equals an, in other words, if f is just every sequence, if you have a sequence defined by a formula, you're going to just replace n by x and you're going to get a function. Okay? That's a function f that I'm talking about here. So this is a function so that the range of the function contains the outputs of this sequence all the time. I'm going to show you a picture now so you can recognize it. But basically, all this means is, for example, if you have the sequence 1 over n, what's the function associated to the sequence 1 over n? That would be the function 1 over x, right? Because when f of n would be equal to 1 over n. If you look at f of x equal 1 over x. So if an is a sequence with f of n equals an, then it follows that the limit of an is the same as the limit of f of x. Then the conclusion is that the limit as n approaches infinity of an equals the limit as x approaches infinity of f of x, which is L. Okay? So either both converge or both diverge. Now, why is this theorem important? Because this now allows us to bring all the techniques from Cal 1 into the sequence world. Because if you want to take the limit of the sequence, maybe this is a very complicated formula, but technically you cannot use L'Hopital's rule here. Why? Because this is not continuous. How is the graph? What's the graph of a sequence? It's just a bunch of dots. Remember, the input is 1 and 2 and 3, so you have a bunch of spaces in the x-axis. So it's just a bunch of dots. So there's no notion of derivative, nothing like that for sequences. But you can pass from sequence to a function, and once you are here, then you have all the techniques that you learned back in Cal 1 to find limits, L'Hopital rule and all of that business. Okay? So always keep this in mind. You just need to make sure that you go from the sequence to the function, and then you can find limits. Let me say, I should have put here as part of the definition. I'm going to bring this down. Just make an arrow in your notes because I want to define the notion of convergence and divergence. I said it, but I didn't write it. So if L exists, Bfx, then this means that. So if if such a number L exists, we say the sequence converges, and if you want to specify, you can say converges to L. Otherwise, we say it diverges. Okay, so to say that a sequence converges or diverges is to say whether the limit exists or not. Okay, that's what it is. Okay, so we already know the notion of convergence of a sequence and therefore divergence. So let's do some examples. Yeah, remember L, I define it to be the limit. So basically, if the limit exists, the sequence converges. If it doesn't exist, the sequence diverges. Remember, L is defined to be, it's a fixed number, which is the limit of the sequence. Okay, if such a number exists. All right, sometimes it doesn't exist, as we're gonna see in the examples. So for example, determine convergence. And let's take a look at some of the ones that we have above. So let's see, number one, let's do something interesting. So let's do the sequence AN is gonna be given by 1 plus 1 over n to the n. Anybody recognizes this? This expression, maybe from pre-calculus? Okay, this exercise is gonna justify what you probably was told in pre-calculus, maybe. You know, you have been using the number e all around, left and right. What is that number? Where is this e coming from? Well, it turns out that e is the limit of this sequence. This is a list of numbers, okay? And this list of numbers gets close to something. That something, we call it e. So e is the limit of the sequence, okay? So let's find it. So determine convergence, and this is our first example, so let's do it. So basically here, I'm just gonna take the limit. If the limit exists, it converges, and it converges to a number, okay? And remember, that just means that the values of the sequence are getting closer and closer to that particular number. So I'm gonna find the limit as n approaches infinity of 1 plus 1 over n to the n. So for this particular one, you could just tell me this is e, because that's the definition of e, okay? But then you need to argue in another way that this converges, which we're gonna learn a theorem later on, which is the, you know, that tells you that if a sequence is monotonic and bounded, it must converge. Just like for the comparison theorem, that we didn't need to actually calculate an integral to be able to tell whether it converges or not by comparing with something else. There are some sequences that may not be easy to calculate the limit, but you can argue that the terms are getting bigger and bigger, and they cannot go beyond a certain point, so it must get close to something, so it converges. I'm going to show you that theorem later on. But anyways, that's how you could argue that this converges to something without having to actually calculate the limit, and then you just define that the limit is e. But we have calculus techniques. We can calculate this limit. And I will use this to show you some techniques of dealing with indeterminate form, okay? Because we didn't get time to discuss much of it last time. Anyways, because notice that this limit, if you calculate this limit, what do we get? What happens to the base? What type of limit is this? When n approaches infinity, what happens to 1 over n? It's 0, so the bottom is 1, and the top is infinity. So this has the form 1 to the infinity. This is an indeterminate form. Remember I mentioned last time there are 7 indeterminate forms, okay? When you take limits, let me write it here, indeterminate forms.
Did you write it above the equal sign?
Huh?
Did you write it above the equal sign?
Oh, because I'm gonna write something else, and what I'm about to write is because again an indeterminate form, so that means I cannot decide right away what the answer is. I need to do some work. So it's good to indicate why I'm gonna do whatever I'm gonna write here. Okay, you can put it 1 to infinity with an arrow or whatever, you know, just to say that what I'm about to write is because I saw 1 to the infinity. That's basically. Okay, but let me just make a pause here. Remember, there are 7 indeterminate forms. They are 0 over 0, infinity over infinity, 0 times infinity, and then we have 1 to the infinity, infinity to a 0, 0 to a 0, and then finally we have infinity minus infinity. That means every time you're taking a limit, if you get one of these guys, you need to do something. Okay, you cannot just decide what the answer is by looking at it. Okay, there is some work that you have to do. What I mean is, for example, if you get infinity plus infinity, well, you can say, well, that's infinity because that's something getting big plus something that's getting big, so the sum is getting big, right? So this is not indeterminate. You can say this is positive infinity, for example. Do you understand what I mean? But if you have infinity minus infinity, you cannot say that because maybe this infinity is smaller than this one, like this one is lower than this one. It could be that this one goes faster, and therefore this would be negative infinity. Or if the first one is faster, then it would be positive infinity. Or if they are more or less the same rate, then this could come out to be a number. Okay? How do you know? Well, you have to calculate it. There are techniques for this. Okay? So the point is that whenever you see any of these 7 forms showing up, you cannot just say, oh, anything to a 0 is 1. So if I see a 0 to a 0, that's 1. But if I see an infinity to a 0, that's 1 as well. No. Okay? Because it really depends how fast these things are, how fast this is growing, how fast this is going to get getting smaller, etc. So that's why we have a theorem that you learn in Calc 1 called L'Hopital's rule, right? L'Hopital's rule allows you to deal with the first two directly, 0 to 0 over 0 and infinity over infinity. Then the idea is that the next one, the 0 times infinity, there is a little trick that you can do that we turn it into either a 0 over 0 or infinity over infinity, okay? And then you can use L'Hopital's rule. And then the next three, there is another trick that you do that allows you to take it into a 0 times infinity situation, and then you use the blue trick to turn it into one of the first two, and you can use L'Hopital's rule, okay? And this one is by itself. So typically, this is a difference of two functions, and then, you either subtract the functions if you can, or use some properties, or factor something, and then it will reduce to one of the previous things, okay? But this is on a case-by-case basis, depending on the expression. The reason why I chose this example first is because this is a 1 to the infinity. So in here, I'm going to show you the three techniques, right? So because I'm here, I'm going to show you how you pass from here to the 0 times infinity. And once you add the 0 times infinity, in the same example, I will show you how you pass from here to one of these two. And then we use L'Hopital's rule, okay? So in this example, we kind of show you the full spectrum to solve this type of limits. But because it's 1 to infinity and I want to use these techniques, eventually I will need to use L'Hopital's rule, and L'Hopital's rule involves derivatives. Derivatives don't make sense in sequences, so we need to pass to the corresponding function, okay? So I'm going to abandon n, I will just put x, okay? And this theorem is the one that allows me to do so. It says that the limit of the sequence, if it exists, is going to be the same as the limit of the corresponding function, okay? So this is the same as the limit as x approaches infinity of 1 plus 1 over x to the x. All I did was, whenever I saw an n, I put an x. But this now allows me to use calculus. All the techniques from Calc 1, okay? All right, so once again, this is a 1 to the infinity situation. So what do we do? Well, that trick. So note, let me show you how we deal with the 1 to the infinity. The idea is the following. I can write any term. So let me say here. So anything, I'm just gonna call it y. So y, I can write it as e to the ln of y. So think about that for a second. What do you know about e and ln? They cancel each other. They are inverse functions, right? So anything that you have, you can always write it as e to the ln of that. Of course, provided that this stuff is positive. If this is negative, then this doesn't make sense because you're going to do ln of something negative, okay? But provided that this is positive, you can always write it as e to the ln of that. Why is this helpful? This is very helpful for this type of indeterminate forms, the ones that are exponential-like. Because by having an ln, that's going to allow me to bring the power down. Remember, logarithms, they bring powers down, okay? So that's why we take advantage of that. So, for example, if you have 1 to the infinity, understand that what I mean by this is 1 represents something that approaches 1, like in our problem is 1 plus 1 over x, and infinity represents something approaching infinity, like in our problem is x, okay? But if you have 1 to the infinity, you can rewrite this as e to the ln of 1 to the infinity. This is the general idea. Then the infinity comes to the front. So this is e to the infinity times ln of 1. Now, what do you know about ln of 1? What is that equal to? 0. So now we turn a 1 to the infinity into a 0 times infinity situation. Do you understand this? So this is now, this right here is now an infinity times 0 situation. Okay? So that's how you go from the green group to the blue group. And you can do the same trick for the other two. Okay? So whenever it's exponential like this, just write as e to the n, bring down the exponent, and it's going to be 0 times infinity. Now, how do we go from 0 times infinity to the other, to any of the other two? Here is the idea. Basically, I'm going to use another fact, which is the point that if you have a times b, I can write this as a over 1 over b. Take a second to digest this. Do you understand it? Yes? Okay, so that's what we use. Because 0 times infinity, now I can rewrite this as, for example, let's say I want to bring the infinity to the bottom, I can write it as 0 over 1 over infinity. Now, what's 1 over infinity? 0. So this now has the form 0 over 0. Yes? Similarly, I could decide to keep the infinity on top and bring the 0 to the bottom. What's 1 over 0? Understand that when we say 1 over 0, it means 1 over something that's getting very small. Okay? So what's that? That's infinity, right? You do 1 over something that's getting smaller and smaller and smaller, your fraction gets bigger, bigger, and bigger. So this now is an infinity over infinity. And then there, we use L'Hopital's rule. Yeah, and we're going to do the example now. So this example that I put up on top is going to involve all of these steps. Because we have a 1 to the infinity, we're first going to pass to a 0 times infinity, and then we're going to use one of these two tricks to go to the form that I can use L'Hopital's rule, and then we'll use L'Hopital's rule. Okay? Which one do you decide to bring to the bottom? Well, at that point, it really depends. Remember, you will have to take derivatives of the top and the bottom. So you may want to have something here that's comfortable. As a general rule, if one of these two terms is a logarithm, you don't want to bring that one to the bottom because then you need to take the derivative of 1 over ln of something. And that may not be fun. Okay? So typically, if you have a polynomial times a logarithm, just leave the term with the logarithm on top and bring the polynomial down. The quotient rule is more friendly there. Okay? So that's a suggestion, but which one you decide to bring to the bottom is up to you. Okay, so as a general idea, so let's go back to the example. So we want to calculate the limit as x approaches infinity of 1 plus 1 over x to the x.
Professor,
yes.
You just said bring whichever one's easier to integrate to the bottom.
To take the derivative. Remember, just think about it. Why is it that we want to do? Why are we doing this? We're doing this because we want to use L'Hopital's rule, right? L'Hopital's rule involves taking the derivative of the top and the derivative of the bottom. You want to make it so that you get something nicer that you can take the derivative of. Okay? You don't want to get something super complicated. All right. So again, we detect that this is 1 to the infinity. So that means we need to do something about it. We already know what needs to be done. So we rewrite this as e to the ln of 1 plus 1 over x to the x. And then we activate the process. This x comes down. So that becomes limit as x approaches infinity of e to the x times ln of 1 plus 1 over x. Now, I want you to realize that when x approaches, as promised, when x approaches infinity, this argument approaches 0, right? Notice that it approaches 0 with positive numbers, so 0 from the right. Sorry, approaches 1, but from the right, because this is 1 over x positive. So this approaches 1 from the right, that means it's going to approach 0 with positive numbers, okay? The point is that this approaches to ln of 1, which is 0, and x is approaching infinity, so this is a 0 times infinity situation. Now, another fact that you learned back in Cal 1 is that when a function is continuous, basically that means that you can pass the limit through. So if you find the limit of e to some power, that's going to be equal to e to the power of whatever this limit is. So you can pass the limit through the function. That's what continuity means, really. So this actually will be the same as e to the limit. You know, if I tell you what's the limit, just thinking about functions, let me just put it like this. What is this limit? Limit of x approaches 1 of e to the x minus 1. What is that limit? 1. Why? What did you do?
1 minus 1 and e to 0.
So you took the limit of x minus 1, and then you evaluated the exponential at that answer. So intrinsically, this is what you did. Right? That's what you did. If you tell me 1 minus 1, what you did was that you found the limit of the top, right? And then you got a result that was 0, so your answer is e to the 0. Yes? So that's what you do with continuous function. You pass the limit through the function. So basically, to calculate this limit, I just need to calculate the limit of the top, and my answer is e raised to that limit. Okay? All right. So this would be the limit of x times ln of 1 plus 1 over x. So all we did here was we changed the equation from a 1 to the infinity, a limit of 1 to the infinity, of a limit that has the form 1 to infinity, to a limit that has the form infinity times 0. Okay? So now let's complete this limit. And remember that our answer is going to be e to the power of whatever that limit is. Okay? Because typically students compute the limit and then you forget that your answer is e to the power. I'm going to compute the limit down here so I don't have to be writing the e every single time. But understand that once I'm done, I have to come back and fill in the box with what the limit should be. So limit as x approaches infinity of x times this guy. Again, what type of limit is this? This is an infinity times 0 situation. So we need to deal with this using the previous technique. So one of these two guys have to be brought to the bottom to turn into either 0 over 0 or infinity over infinity. As I suggested, the term with the ln, you should leave it alone. So I'm going to keep that guy alone. I'm going to bring the x to the bottom. So this term stays here, and then the x, I'm going to write it as 1 over x in the denominator. Just doing an algebraic manipulation. I haven't done anything weird. The point is that this now has a form 0 on top and 0 in the bottom, right? 0 over 0. So we can use L'Hopital's rule. So whenever you use L'Hopital's rule, you should indicate that. So I like to indicate that on top of my equal sign, I put an LH, just letting you know that I'm about to use L'Hopital's rule. Okay? All right, so L'Hopital's rule says that when you have 0 over 0 or infinity over infinity, you can exchange this limit for another one that will be equal, in which the top is replaced by its derivative and the bottom is replaced by its derivative. Okay? So as the limit as x approaches infinity of, now what's the derivative of the top? It would be 1 over 1 plus 1 over x times derivative of the inside. Remember, we need to use chain rule. The derivative of the inside is 0 plus, so it's just the 1 doesn't count. Derivative of 1 over x, that's negative 1 over x squared. Right? Derivative of 1 over x is negative 1 over x squared. 1 over x is x to a negative 1. Bring down the power, subtract, so you get negative x to a negative 2, which is negative 1 over x squared. That's the derivative of the top, and then the derivative of the bottom is negative 1 over x squared. Good. So this guy cancel with this, and therefore we have limit as x approaches infinity of 1 over 1 plus 1 over x. And what is this limit? So this piece here goes to 0, right? So we get 1 over 1 plus 0. That's just 1. So our answer is e to the 1. Remember, this is just that piece. So the answer is e to the 1, which is e, as expected. I mean, that's how we define the number e, as a limit of this sequence. Okay? And now we are kind of verifying this process. Okay. Questions? Huh?
Okay. No, I forgot about the box. Like you said, everyone forgets about it.
So the sequence 1 plus 1 over n to the n from 1 to infinity converges to E. Great. Questions?
Could you just write the definition of the Hoppler's rule so I can rewrite it in my notes?
Oh, so Hospitals, basically what it says is that the limit, so if the limit as x approaches a, okay, I'm gonna write two definitions in one. Okay, I'm gonna write something, but then understand that you can replace a by infinity, okay, by plus or minus infinity. So if limit as x approaches a of f of x over g of x equals 0 over 0 or infinity over infinity, and when I say infinity over infinity, it could be 4 different choices because it's plus or minus infinity, plus or minus infinity. So, you know, positive on top, negative in the bottom, or to negative to positive, and all that. Okay, so if the limit of f over g gives you 0 over 0 or infinity over infinity, and of course the function f and g have to be differentiable, like you have to be able to take derivative and all of that business, okay? But it says if the limit is 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x will be the same as the limit as x approaches a of f prime of x over g prime of x. But it basically tells you that you can exchange the top by its derivative and the bottom by its derivative and then take the derivative. That's what it says. And also the comment is that if you replace a by infinity, it also applies. So in the above, a could also be infinity, okay? So it's as you approach a point, but also as you approach infinity. We use it at infinity in the above. Okay? All right, again, this was just an excuse to bring this up, just to remind you of this, because you may need to calculate limits, like when you're doing your integrals and so on, and then you need to know that you have all of these techniques available, okay? All right, questions for this example? Did you understand how we calculated the limit? Yes? All right, so let's do another one. Oh, and by the way, all the properties that you know about limits from functions, I don't want to rewrite them, but they apply here. Like if a limit exists, and then you have a constant times a function, then you can put the constant out of a limit. The limit of a sum is the sum of the limits. The limit of the difference is the difference of the limits, and all of that business. Okay? So I would just say all properties. So remark, all arithmetic is sum, addition, multiplication, division, okay? All arithmetic properties of limits or functions carry over to sequences, okay? So, all right, so let's do another example. And let's actually take the previous examples that I gave you to list the elements, and then let's figure out where the sequence converges or not. So how about the sequence 2 plus -1 to the n? What can you say about this sequence? Does it converge or diverge? So whenever you're going to study a sequence, it's always a good idea to write down some terms, okay? So remember, we wrote down some terms. This sequence turned out to be 3, 1, so we start at 0. So it turned out to be 3, 1, 3, 1, so on. So what can you say about this sequence? Converges or diverges? Why?
Because there's nothing that it ends up at.
It doesn't get close to anything, right? I mean, if you want, it's getting close to two things. No matter how far away you go into a sequence, you will always find a bunch of 3s, but you will always find a bunch of 1s. So it's getting close to 3 and close to 1 at the same time. So it's not getting close to anything in particular. Okay, there's no one number L that you can say that's getting closer to that, because 3 and 1, they are far away. Do you understand this?
It'd be like sinusoidal, right?
Yeah, it's actually, you know, dots. If you think about the graph of the sequence is like this. See, 1, 2, 3, 4. Let's say this is 1, 3 is over here. So it starts with a dot here, and a dot here, and a dot here, and a dot here, and so on. Oh, yeah, wait. It's 0. So a dot here, here, and here, down here, and here, you know, and so on. That's what the sequence is, a bunch of dots. Not getting close to anything. As you go far away into the x-axis, which is equivalent to say n goes to infinity, you're not getting closer to any number. Yes?
It only uses whole numbers, correct? There's no like 0.5 or anything like
No,
that.
because n is a counter. It is the first element, second element.
Okay.
You know, what do you mean by the 0.5 element?
Yeah.
Right? So that's why it's a function from the natural numbers to whatever set. Basically, that's a way of telling you that you have a sequence of elements. That's the word sequence. So first element, second element is a list. So that's what it is. Okay, so this diverges since the limit of an does not exist, right? Doesn't get close to anything, so this limit does not exist. Do you understand this?
Right, so we can, a way we can determine if it's divergent is we take the terms of the sequence.
Well, you always, whenever we're studying the sequence, right? So if it's not something that you can manipulate immediately from this formula, because you know this negative 1 to the end, you're gonna get negative 1 to infinity. What is that? That's not in the determinant form. The determinant form is 1 to infinity, but not negative 1 to infinity. Okay. So what is that? Well, let me take a step back and look at the sequence. And then it turns out that this sequence is just a bunch of 3s and 1s. 3, 1, 3, 1, 3, 1, 3, 1. So there's really nothing to do. It's not getting close to anything. Just go back to the basics. That's why it's good to know the definition. Limit means that you're getting closer and closer to something, as n is very big. Okay? And many times you can just detect it from the very beginning. Okay? All right.
There was something on the desk, a sheet of paper, something, a lesson plan, something like that.
I just did. There's something.
Thanks a lot.
Okay. All right, so let's take a look at this one. How about n over 1 minus 2n? And this was from 0 to infinity, right? So what can we say about this sequence? Can we calculate its limit? I mean, that's a formula, so the question is, can we calculate its limit? The answer is yes. It's a rational, I mean, if you think of the function, this would be a rational function. Degree of the top is equal to the degree of the bottom. So what's the limit? It's a ratio of the leading coefficient. So this is negative 1/2. Yes? Remember when you study rational functions? No? X over 1 minus 2x. If I ask you to graph this function, what do? This is back from pre-calculus. You need to find the asymptotes. There's a vertical asymptote, which is the 0 of the denominator, right? Namely 1/2. And there's a horizontal asymptote, which is the end behavior of the function. And what is it? You have to look at degrees. Because the degrees are the same, it's a ratio of the leading coefficient. Okay. So it's negative 1/2, right? Yeah. Or if you want, you can use L'Hopital rule. The derivative of the top is 1 because it's infinity over negative infinity, right? Derivative of the top is 1, derivative of the bottom is negative 2. So negative 1/2. There are many ways to see why is that. But actually, instead of bringing all of these big techniques into the picture, we can do this way easy by just doing some algebra and manipulations. So let me show you. You can do it however you want, okay? The faster way is just to recognize that the corresponding function is rational. But here is something cleaner. I'm going to divide top and bottom by n. So dividing by n is going to be 1 over n minus 2. Do you see it? If I divide top and bottom by n, now take the limit. What happens when n approaches infinity? This goes to 0. So you get 1 over 0 minus 2, which is negative a half. Okay? But again, you can also do it just thinking about rational function, L'Hopital rule, and all of that business, but there's no need to bring all of that because here we can do it pretty easy. You do it however you want. This is actually how you prove that theorem for rational function. In pre-calculus you learn a theorem about rational functions for the horizontal asymptotes, and it turns out that at the end of the day, you're just looking at degrees, right? How do you justify that? This is the type of things that you do. You divide top and bottom by the leading term of the highest degree, of the term with highest degree, and then you observe what happens. Most of the guys go to 0, and then it just turns out that it's equal to the ratio of the leading terms, and then you make a conclusion there for the degrees. Okay, so we got the limit. The limit is negative 1/2. So what can we conclude about the sequence? Converges or diverges? Converges. So the sequence converges to what? Converges to negative 1/2. So remember, all we're saying here is that eventually, maybe not at the beginning, but eventually, the terms of the sequence are going to be very, very, very close to this. Okay? Eventually, it's going to be very, very close to this. And the farther into the sequence you go, the closer you're going to get to that. Okay. Questions? Do you understand this? Again, you understand limits, right? You did limits. I don't know. I see your faces like if I'm talking about a new concept. This should not be a new concept. Is this a new concept? This is not new, right?
It's not available, it wasn't obtained.
Yeah, it was before like a week ago. Last time I did limits was in like October. It was a while ago.
But it's just in calculus, limit is a central. In calculus 1, limit is like it's the center of everything. I mean, even the derivative is defined as a limit.
Yeah.
The limit of the difference quotient, and
Yeah, we went over limits in the beginning of calculus 1, and then we went to derivatives and never really did anything with limits again. After like a month.
I mean, even an integral is a limit, right?
The thing is, we don't see it as a limit, even though it is one. We see it as a
Yeah.
variable.
But in calculus 1, when you do derivative, there should be a portion which is about applications of derivative. That's when you talk about graphing functions, optimization, maximum, minimum, all of that. And in there, you talk about L'Hopital rule, right? So you see limits again. So yes, you went through all the technicality of derivative of that business, but then limits made their entrance again with L'Hopital rule.
Right.
Then you enter into a little bit of integrals and you stop. That's usually how what should happen in Cal 1. You start with limits, continuity, beginning derivative, which has limits, right? But so at some point, it's a mechanical process, so you don't do too much limits. Then once you know derivative, now let's apply this knowledge. So you apply it to optimization problems, graphing functions, calculation of limits, so back to limits, using L'Hopital's rule and all of that business. And then you go into integrals, and you stop, waiting anxiously to come to Cal 2.
Anxiously, yes.
So that's normally what happens. So you revisit limit more or less towards the end, or should revisit limit. Anyways, that's the reason why I took time here and explaining you this, because you need to know these things. You need to know these things. Okay, but most of the limits that you're gonna have, they should not be that painful. Okay. All right. How about this one? N squared. I mean, I'm just putting the examples that we had originally. Okay. So n squared over 2 to the n minus 1. Oh, from 1, right? But it doesn't really matter, because remember, when you talk about convergence, it's really a limit as n approaches infinity. So the convergence of the sequence is the same as the convergence of the sequence if I start at 1,000. Because anyways, the question is what happens when you're super far away down the line.
What's the end result?
So it doesn't really matter. The beginning terms, the sequence can be doing whatever it wants at the beginning. The question is eventually, does it get closer to something? Does it stabilizes to something? Okay. we're gonna see that in series. That you can just drop some terms. If there are some terms that are giving you issues at the beginning, just drop them and then analyze what happens until it becomes nice, when it starts to become nice. All right, so what's going on here? So this is the limit as n approaches infinity of n squared over 2 to the n minus 1. Once again, we are trying to figure out convergence, and then we're jumping into trying to compute the limit immediately. Okay. All right, so we can use, notice that this is an infinity over infinity situation. Okay, so I want to use L'Hopital's rule, but technically I need to have a function. I cannot do this at the sequence level. I mean, this is a technical step. Okay, I mean, if you do it, I mean, you're gonna get the answer. It's just that you need to understand that n squared doesn't have a derivative, right? Because that's just a bunch of dots. So to be correct, you need to pass to the function, and now you can use L'Hopital's rule. All right, so also you can argue by growth rates. I mean, you know that exponentials are among the faster growing functions. In particular, exponentials, they grow faster than polynomials. So we're expecting this to be 0, right? Because the top grows slower. But anyways, let's just do it. It's just that we need to use L'Hopital's rule twice. So derivative of the bottom of the top is 2x. Derivative of the bottom is 2x, 2 to the x times ln of 2, right? So once again, 0 over 0. So we use L'Hopital's rule one more time. So that's the reason why exponentials always win over polynomials, because polynomials, after finitely many repetitions of L'Hopital's rule, you will get a number on top. How many times? As many times as the degree. You will need to take the L'Hopital's rule. But exponentials, you just keep getting exponentials, right? It's just that this factor of ln of the base pops up. But the exponential never disappears from the denominator. At the top eventually becomes a number, so that's why eventually you're going to have a number over infinity that's just 0, right? But again, you could take that from the beginning if you know that exponentials grow faster than polynomials. Okay, so the bottom goes way faster, so eventually the denominator is going to be way bigger than the top, so it's going to go to 0.
Why is it squared?
What's the derivative of 2 to the x? It's 2 to the x times ln of 2, but then you multiply with another ln of 2, that's what you get. I'm taking the derivative of this now. That's a constant, that's there, but then the derivative of 2 to the x is 2 to the x times another ln of 2.
Oh, so you did it 2 times.
1, 2.
Yeah.
Okay, so converges or diverges?
Converges to 0.
So converges to 0. And what do we do, for example, in something like this that we don't even have a formula? But we could still ask the question. I mean, this is a sequence, so I can ask you for is convergence. Remember, this is the Fibonacci sequence. Wait, let's just say D1, D2. I mean, it doesn't matter. The index doesn't really matter when you start at 1 or 0. You just need to be consistent. If I put 0, 1, then I will have to put 2 in here. Right? Okay, so what do you think? What's going on here? This is a good, a good example in which, by looking at the terms, you can tell what's going on. So what are the terms? This. So what do you see that's happening? Right, I mean, the elements of the sequence, they're getting bigger and bigger, and they're not going to stop growing. I mean, the next term is the sum of the previous two, and you're always adding positive stuff. So this sequence is not going to get close to anything, and it's not going to go down to, it's not going to decrease. So this diverges to infinity. Do you understand this? Without doing any form of calculation, just by looking at what's going on here, the way the sequence is defined, it's clear that this is going to diverge to infinity. Yes, so we have a language for this. We will say this sequence is increasing and is unbounded. Unbounded means there is no number that the sequence cannot go beyond. Okay, it doesn't have a wall, if you will. Okay, that's what it means to be unbounded. So it's There's no number that will cut the sequence. For example, 1 over x is 1 over n is bounded by 1. 1 over n will never be beyond 1. It just gets smaller and smaller, for example. Okay. So the above sequence. So this sequence keeps I should say the terms of the sequence keeps getting bigger and bigger. The terms of the sequence get bigger and bigger. And they don't stop growing. So it diverges to infinity. So it diverges. And then, you know, when it's infinity, we like to say it because basically when we say that it diverges to infinity, we're basically saying the terms are getting bigger. But remember, the previous examples, it diverges, but not because the terms are getting bigger, just because it's oscillating between different numbers, right? The behavior is different. That one was bounded because that one cannot go beyond 3 or below 1. So that sequence was bounded, right? But still, it did not converge. Now, this one diverges, but not because of that. It's just because the terms keep getting bigger and bigger and bigger. Okay, so we typically like to say diverges to infinity just to say that means that the terms get bigger and bigger. Okay, questions? There?
What?
Meet Franklin. Yeah, because usually you are the one that's usually interacting with us, so you are famous in the classroom. Yeah, there is Franklin. So it's good. It's good. It's good. You see, like he was missing you.
I was worried.
Yeah.
I only have one class that is physical. I literally can't come to my other Tuesday, Thursday classes.
I see.
So it's all that gas for me. Just
Yeah, it's okay. It's okay. All right. So let's see. I have something interesting here. Remember squeeze theorem from Kawan? It carries over also. Okay. So. Nope.
Yeah, the one that we did.
The squeeze theorem also applies. I'm gonna write it down. Also applies to sequences. Okay. Basically it says this. So theorem. So suppose that you have 3 sequences. Okay. So let AN, BN, CN be 3 sequences. Now, technically, you know, at the beginning, these sequences may be doing whatever they want. But if eventually they satisfy a certain inequality, that's what we care about. So that's what I'm going to do. So that eventually is what I'm about to write, okay, in a mathematical term. Just so that you don't get, but, you know, we need to know how to mathematically write some stuff. So eventually means if you go far into the sequence for each of them, then you will get the inequalities that we need. So I want Bn to be between An and Cn, okay? That inequality to be satisfied all the time. So let these guys be 3 sequences, and then suppose there is a positive number m such that for all n, I mean, this number could just be 0 or 1, okay? But maybe at the beginning, these sequences are going crazy and they have no control with each other. But eventually, they stabilize. That's what I'm saying here. Suppose there is a positive m such that for all n greater than or equal than m, we have that an is less than or equal than bn, which is less than or equal than cn. Okay? So if this happens from the very beginning, perfect. But it could be that at the beginning the terms of an are bigger and all of that. But eventually, if they come down and we have this behavior at, at some point, and then the behavior doesn't change, that's the situation that we're talking about. Okay. So the tail of the sequences satisfy this condition. That's what I'm saying here. So if we have this, and if we have this inequality, and the outside sequences, so suppose there is this, so that for all n we have this, and we have this. Now, if the outside sequences, so if the limit as n approaches infinity of an happens to be the same as the limit as n approaches infinity, Cn, let's say they're both equal to L, then even if we have no control of what Bn is, we are able to deduce that because it's always between these two guys, and these two guys are getting closer towards the same number, the one in the middle has no other choice to go to the same number. That's why it's called the squeeze theorem. Some places you call it sandwich theorem. You may read it like that. It's a sandwich theorem. It's basically squeeze or sandwich between the two. Okay? It could be doing crazy stuff, but eventually it has to stabilize towards L because the bottom and the top, they go towards L. And you are in the middle, you have to come down and go towards L as well. So if this happens, then the limit as n approaches infinity of Bn equals L as well. Okay? So typically, I will illustrate like this. So we have An less than or equal than Bn less than or equal than Cn, and then we just use the arrow notation. This goes to L, this goes to L, therefore the one in the middle has to go to L as well. Okay? So, and it's understood that with these arrows we mean as n approaches infinity. Okay, so that's typically how we denote the squeeze theorem. Okay, so let's put this to good use. Let me give you an example, and I'm gonna use a theorem that's gonna be helpful for us later on. So theorem, this is the absolute value theorem. So absolute value theorem. So suppose that you have a sequence. Let An be a sequence, and maybe this sequence you don't know how to control it very well. So here is the example that I'm gonna get ahead myself, but let me put it here. Determine the convergence of, and then the sequence that I want to analyze is An equals -1 to the n over n factorial. Okay. So, the sequence is oscillating between positive and negative values. But, intrinsically, you should realize that this should go to 0. Why? Because even though it's jumping between positive and negative, the bigger n gets, what happens to the denominator? It's growing larger and larger and larger. So you're going towards 0, but sometimes above the x-axis, sometimes below the x-axis, above, below, but you're getting towards 0 anyways. So we're expecting that we're going to be close to 0. When n approaches infinity, the limit will be 0. Okay? So we're expecting that the answer is 0, but again, how do you calculate this? Well, this theorem allows you to say just that. Okay, so let me write it down.
Would it just be that you put An as, well, in this case An, but you put one of them as 1 over n, and the other one as -1 over n?
Very good. That's exactly what I'm about to do now, but in general. Yeah, good. So let's let An be a sequence. Now, if, let's say that maybe we don't know what the sequence, maybe the sequence is going a little bit crazy, like changing signs, like our sequence above. But maybe if after taking absolute value, it behaves nice. Like for example, if I take the absolute value of that one, I get 1 over n factorial, right? And we know that would be 0, right? The sequence. So if the limit of the absolute value equals 0, then the limit of the original sequence is also 0. This is gonna have remarkable consequences For example, we're gonna use this for series as well. All right, so let's prove this, and the proof is very nice and easy. And the remark is to know that for any n, the sequence an is always less than or equal than its absolute value version and the negative of its absolute value. In other words, any number that you pick is always between its positive version and its negative version. It's actually one of the two, right? We actually have equality. It's actually equality, but it's still true that every term in this sequence is between these two. Do you agree with this? Do you understand this statement? Yes? Okay. What's the limit of the first sequence? What's the limit of this? Look at the hypothesis. Remember the hypothesis. The hypothesis is if this happens, right? So we are assuming that this is happening. Okay? Do you understand this? Okay. So this is statement of the form if then. So that means provided that the limit of the absolute value is 0, then the conclusion is the limit of the sequence itself must be 0, right? So you're taking that for granted. So the proof is, okay, we have to assume this, we need to prove this. Okay, that's how you prove if-then statements. You assume the if part, and then you prove the then part. So I guess let me do a little bit more formally. Assume that the limit as n approaches infinity of an equals 0. Okay. Okay, then note that for any n we have this inequality, and then what's the limit of this guy? That's going to be 0, right? This one is also 0. So what can we deduce about our sequence an? It has to be 0, right? As n approaches infinity. So then, by the squeeze theorem, the limit must be 0. Done. Okay, so it's a very easy argument, but it actually has a nice consequences. For example, we can use it now to easily determine the convergence of this sequence. Okay, so you just have to remark that when you look at the absolute value, that's just 1 over n factorial, right? Because the negative 1 over n, the alternating sign business, is gone, and this certainly goes to 0 as n approaches infinity, right? Because this is like a super enhanced version of 1 over n. It goes way faster to 0. So it goes to 0 as n approaches infinity. So by the above theorem, the limit as n approaches infinity of an must be 0 as well. Okay? So the answer is converges to 0. Say that again?
Determine convergence is minus
of an. That's an f, no? Of. Okay. Questions? All right. So,
Just one note, was in the absolute value, is that one supposed to be without its exponent anymore?
say that again?
Note absolute value AMN, is one supposed to have an exponent? We're gonna lose it?
No. Because this negative 1 to the n, all it's doing is giving you +1, -1, +1, -1, +1, -1. By doing absolute value, you're keeping the ones, and the -1, you're turning them into ones. So it's just 1. Right? Remember, -1 over n is just a way of alternating sign, because n is something that runs continuously. So that's just a way of having positive, negative, positive, negative, positive, negative. We make absolute value, you're just making everything positive.
What does it mean n factorial?
Oh, that's the product from n all the way down to 1. So n factorial equals n times n minus 1 times n minus 2 times 2 times 1. So for example, 3 factorial equals 3 times 2 times 1, which is 6. And by definition, 0 factorial is 1. This is by definition. And for example, you can define recursively factorial, like, n factorial can be defined as n times n minus 1 factorial. Because that product, this is the n, and then this product, n minus 1 all the way down to 1, you can rewrite it as n minus 1 factorial. And this helps you a lot when you need to simplify expressions involving factorial. We're going to have to deal with this later on when we talk about series. I mean, all of this is so that we are ready to talk about series. That's why it's the first section.
Is that also like a Calc 1 thing that we spaced on?
So,
It seems familiar. But
in precalculus use of factorial, yeah. Anyways, we're going to deal with that. Don't worry.
That was pre-COVID times.
Okay, so are you okay with this? More or less. Again, this is just familiar concept. I mean, you know this. It's a list of elements. You're getting close to something. You already know what a limit is. You can bring other techniques from Calc 1. At least you have seen it. Okay, let me rephrase. You have seen it, right? So it should not be something alien to you, what we have done so far. Now, the only thing that I'm missing here to tell you is, again, there are ways to tell whether a sequence converges or not without having to compute the limit. But for that, we need to understand what it means for a sequence to be increasing or decreasing. Okay, that's called monotonic. When a sequence is increasing, we say it's monotonic increasing, and decreasing is monotonic decreasing. So monotonic is either going up or down. So the theorem means if a sequence is monotonic, so it could go up or down, and bounded, then it must converge. Okay, but I guess I'll tell you this next time because it's already true. So here is a little post after the exam. Don't worry about this now. So here is a little question for you. How about this sequence? Square root of 3, 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 and so on. Okay? And basically nesting square root of 3 is one inside the other. Okay? Let's see, do I want to do it like that or with a plus? Okay, let's keep it with the plus. Let's keep it simple. This sequence. So something interesting to note is that you can define this recursively. So note an. So you can say that a1 is equal to square root of 3, and then an you can define as the square root of 3 times an minus 1 for n greater than or equal than 2. So basically, the second term is square root of 3 times the previous term. The next term is the square root of 3 times the previous term. You see? And so on. So this is a recursive way of defining this. Determine whether it converges or not. Try to determine whether it converges or not.
It seems like that's just a reconfigured Fibonacci.
Well, this is a recursive definition.
I guess.
So determine its convergence.
Yeah. I'm with you on that.
All right.
So determine whether it converges or diverges, and if it converges, you need to tell me to what. If it diverges, well, it diverges, but you need to justify something. So next time, and the theorem that we're going to discuss, we're going to be able to use that theorem to decide whether this converges or not. Okay? And then the good thing is that if we know that it converges, then it's very easy to find the limit in this kind of problems. Because an observation is that if it converges, then that means the limit exists. If the limit exists, then these are two sequences. An is a sequence, an minus 1 is another sequence. Yes? They're not the same sequence. This is part of this one, but they're not exactly the same. The terms are not the same. Sequence to be the same, they have to be the same. This sequence is basically one step behind this one. Do you understand this? So for example, the A2 here is the A1 is the second term of this sequence is the first term of this one. Yes?
Right.
And the third term of this one is the second term of this one. And so on. So this sequence is always one step behind this one. You understand this? But do they have the same limit? They have to. I mean, you have this sequence, and this one is just one step behind. Imagine that that we are tied by a rope.
Right.
Wherever you go, I'm gonna go. So if an gets close to something, then this one has to get close to the same thing as well. Because the difference is just one term. Do you understand this? So if you convince yourself that this converges, then you can say, okay, it converges to something, then you take, and then you can take the limit and then solve a quadratic equation. Because then, you know, okay, I don't want to spoil it. I'm gonna leave it there.
You can just spoil it for ourselves. You know?
You know, basically you get L equals square root of 3 times L, right? When you take the limit and then solve the equation. So L squared equals 3L. So L times L minus 3. So you have two solutions, either 0 or 3. This doesn't make sense because the terms, as you can see, they are getting bigger. This is something you need to argue, that the terms get bigger, okay? And therefore, this actually converges to 3. But first, to be able to write the linear calculation, you need to argue that this number exists. Because if this number doesn't exist, then what are we doing here? And that's why we need the theorem that I'm mentioning that we're going to discuss next time. Okay? So next time we do that and we begin with series. If you're bored in the weekend, you have this question while you're sailing. Here is another question if you're bored, and this is going to motivate series. Okay? Here is a little problem. Take a square. Half a square. Side 1. Okay? Split it in 4. No, because I want you to think about this. Split the square in 4 and look at the area of one of the 4 pieces. Then take an empty square and do the same thing again. Split it in 4, look at the area of one of the pieces. And hopefully you understand that we can keep on doing this indefinitely, right? The question is find the area of the shade, find the shaded area. Find the shaded area.
So this wants to find the A of n for the sequence.
Find the shaded area. Just think about it. We will solve it next class. We'll solve it next class. But if you're bored at some point, you know, it's good to start thinking about it. So whatever we discuss next class, it hopefully makes sense. So this is what, you know, we're gonna use infinite series to solve this problem because this problem leads to an infinite sum. So then the natural question is, how do we make sense of an infinite sum?